Before I start, I just have a very nice paper here without a name. So if you recognize this very nice handwriting, let me know. Today we're going to talk about inverse trig functions. I was thinking about the kind of the arc of this class, or the subject, and we're past the, what do they call that in the novel? The high point? The climax, yes, we're past the climax, the denouement, I think we call it. We're kind of filling in things. And this is pretty neat, actually, what we're going to do. We'll go over. I guess we have a few more subjects to fill in. In trigonometry, kind of close it all up. And then if there's time, we'll have kind of a sequel. But we'll leave that for later. So we've already talked about inverse functions a fair amount. Just going to remind you that we have a function like f of x equals x squared, of course, is our parabola, that we have to think a little when we find its inverse. F of x equals x squared, just the way I described it here on all real numbers, is not a one-to-one function. Can anyone tell me the rule we use?
Horizontal.
Yeah, it fails the horizontal line test. Right. So, in order to find an inverse function, we first want to make this into a one-to-one function. We can do that by setting the domain to be x between 0 and infinity. In other words, we kind of erase this portion of the function. So now we just have a one-to-one function. And, of course, the graph of that function will just be a reflection along the line y equals x here. And if we use our technique for finding the rule, we would say, well, y equals x squared, but we would switch the x and y. And then we would solve for y, and we would find the square root of x. The positive square root of x being this side. Negative square root of x would be like this, but if we had that, it wouldn't be a function. I want to say it wouldn't be a function, but we could still describe this. We could describe this as plus or minus x. For each x we'd have, except 0, we'd have two values, and it wouldn't be a function. It would be what we would call just merely a relation or a mapping. And I just want to point out one other thing, which is when we look at the domain and the range of the original function, I guess that's the same thing, right? This isn't a good example, but the domain and range of y equals the square root of x is just going to have these, or someone points it out, y's between 0 and infinity. That this is just switching these two. Now they're the same, so it's not really obvious. But it will become obvious when we talk about trig functions. So why don't we just go right ahead and take a look at our sine function. It kind of looks like this. It's defined that all reals has a domain of all reals, but it has a range just between -1 and 1. Now, if we were to invert the graph, well, my graphing program tells me that I have to fix this a little to get it to look right. Instead, going in this direction, we go off in these directions. And not drawn very well, but you can see immediately it's going to fail the vertical line test very badly. It's not at all a function. But if you think about it, it does fit the idea that if I'm looking for the inverse, say I want to say what's the inverse sine of a half? If I ask the question this way, what angles have a sine of a half? There are going to be infinitely many of them. Right? If I pick a point here at a half and draw a vertical line, it will go through infinitely many points, which are all angles whose sine is a half. So how am I going to thread this needle? Well, for starters, I want to go back to my original function. Let's see. I guess I'll just start clean here. And I want to restrict the domain, the x values, with two properties. One is I want it to my domain to hit everywhere on the range, and I want it to be continuous. I just want it to be one interval. If I start off at 0 and go this way, I have a problem, which is up to, say, pi over 2, I'm doing fine. But once I get past pi over 2, the values, the horizontal line values that I'm going to hit, they're going to start repeating. I could kind of jump over here, but then I wouldn't have a single interval. So the way to do this is not to start at 0, but to start over here at minus pi over 2. That is, I'm going to restrict my domain on the sine function. I'm just going to look at the sine function with a domain from negative pi over 2 to pi over 2. Or if you like, from negative 90 degrees to 90 degrees. And now this is one contiguous domain, and it has the feature that I hit each of these points. So when I switch, and I create my sine function this way, I'm not drawing very well here. Now my inverse sine function is a function. It passes the vertical line test. So that tells me that what? That tells me that my domain on this function is going to be from -1 to 1. But my range is going to be from -π/2 to π/2. Okay. This is actually an arbitrary decision. Right? I could just as well have picked an interval out here, 2π greater, and said, okay, the range on my sine inverse is going to be 2π minus π/2 and 2π plus π/2. But there's nothing absolute in math about this. It's just a choice we make. It's just an arbitrary choice. And I want to encourage anyone who has a calculator handy, if you will put it into, let's put it into degree mode. Go ahead, pull it out, try it. If you don't have one, look on with your neighbor. So we're going to get an inverse sine function. Let's take an inverse sine function of -1/2, right? So that's second sine, and I'm just going to put in 0.5. And what do I get? That's not what I wanted to do. I'm going to say second inverse sine minus 0.5. Okay, I get -30. In other words, I put -1/2 here, and I get -30. If you put in 1/2, you'll see you also will get 30 degrees. Right? So what I'm telling you about this arbitrary decision is not maybe arbitrary, but it's very common. All your calculators will do this. Okay, a little notation here. So let's be very careful when we write this. One of the ways we write this inverse function is just like this: sine to the -1 of x. Right? Be very careful. This is not 1/sine of x. Right? This is confusing notation, to say the least, but it's the way it's done. A little less confusing. A little less confusing is to use arcsine of x. These mean exactly the same thing. And you'll see this in our cosine, our tangent, our cotangent, and so forth. Lastly, there's some notation. We're not going to use it, but you could run into it. Sometimes we'll write this, arcsine, but with a capital A. This is not a function, specifically. This is a relation. So whereas the inverse sine of -1/2 is most definitely -30 degrees, or -π/2. over 6. Same with arc sine of minus a half. The arc sine capital A, which is the relation, doesn't have, since it's not a function, it doesn't have this restriction. So it's going to be minus 30 degrees, but it's going to have other values. For example, it's going to have minus 30 plus 360, or for that matter, 360 times n. There's another value it's going to have, set of values it's going to have too. We're going to look at those, so I'm not going to go there now. But I just want you to be, again, very careful about this notation, especially this. Keep in mind if I wanted to use this minus 1 to mean reciprocal, I could say sine of x to the minus 1, that would be the sine of 1 over x. Or if I really want to find the reciprocal of the sine of x, I would put that in parentheses and put the minus 1 here. So that would be 1 over sine of x. I've seen books where they say, well, you could put minus 1 here, and I think that would be a little scary, a little ambiguous. Does that mean this or this? Sorry, 1 over x. Okay, any questions on notation before we go forward? Okay. This might be good to create a little chart here. Inverse sine of x. Domain is from minus 1 to 1. The range is from, just say degrees for now, minus 90 degrees to 90 degrees, or from minus pi over 2 to pi. Now when we go and we look at the cosine function, we want to put the same kind of restriction on it, right? We want an inverse cosine that is just one solid interval. We don't want it to be a piecewise function. And we want it to cover the entire range. Well, in the case of the cosine, it's a little more convenient. We can just take, the domain of the cosine, we can restrict it from 0 to pi, or 0 to 180 degrees here. And you see, we will cover the entire range of values. So this is the inverse cosine of x. Let's put that in our chart here. Again, it's going to have the same domain, but its range is now from 0 to 180 degrees. And again, you're welcome. Try any value between minus 1 and 1 with your calculator. You're going to find, from the cosine inverse function, you will get a positive value. And this isn't math, but I feel compelled to remind you, check your mode on your calculator when you do this. Because if you're, well, let's just do an example here. We'll put it into the radian mode for a second. So if I now say cosine inverse of what? I get the value 1.47. What is that? It's not degrees, right? But you might misinterpret that if you're not careful about the mode. That's a radian measure. That's somewhere over here. 47 radians. I'm sorry. I'm not looking at the right. Looking for where the cosine is 0.1. Okay, so I look here. Yes, I get 1.47. That makes sense. I even get mixed up about this too. You know, when you're switching back and forth between these functions that are inverses, how do you look at the graph here, right? Okay. So that's the sine and the cosine. When we get to the tangent, things are a little different. Recall, tangent function looks like this. Of course, periodic. But every can you recall the period of the tangent for me? It's pi, right? It's not 2 pi, right? It repeats every pi. So it also, it's going to go between minus pi over 2 and pi over 2 here. And if we invert this, right, what's it going to look like? Well, we're going to have this branch. It's going to look like this. But now you're going to have a horizontal asymptote like this. Well, that's not so bad, actually, because we can take this branch here, right? We restrict the domain on the tangent function now between pi and between minus pi over 2 and pi. We take this piece. Now what happens? Well, now we have an inverse tangent function. Its domain is what? Well, its range we know is just like the sine. It's between 90 degrees and minus 90 degrees. What's the domain on the tangent function, the inverse tangent function? The other way of asking this is, what's the range on this piece of the tangent function? Under the, it's all real numbers, yeah. That's nice because that tells you you can plug in any value now for the inverse tangent function. You'll get something. You'll get something between minus 90 and 90 degrees. Okay? Okay, these are the three main inverse functions you need to know about. The other three functions have inverses too. they're a little more complicated. Let's take a look. Let's first look at the inverse cotangent function. So the inverse cotangent function kind of looks like the tangent function. Superficially. Except it kind of goes in the reverse direction. And it's moved over, right? It's not defined at 0 because the cosine of, because the sine of 0 is 0. So it's an asymptote at the axis. So where do you think we're going to restrict the domain? Just taking a look at that diagram, it would be a smart place to draw the line, so to speak. Yeah, I want to restrict the domain. This is the cotangent function. And I want to restrict its domain. I want to restrict the x's so that I end up with a one-to-one function. Right? This clearly is not one-to-one. If I draw a horizontal line, I pass through an infinite number of points. So all I want to do is restrict this so when I pass a horizontal line through, it only goes through one point.
Would you just use 0 to pi?
Yeah, absolutely. 0 to pi. What's its domain then going to be? What's the domain of the inverse function? Or conversely, what's the range of this restricted cotangent function? Any thoughts? I know this seems a little arcane. When we get to actually using this, it'll be a little easier, but I still want to emphasize this because this is the tricky part of the inverse functions. Some places they're not going to be defined, right? We clearly have a restriction here on their domain, right, which is the range of the sine and the cosine, right? The tangent is nice because the tangent, the range on the tangent is all reals, so the domain on the inverse is the same thing. Anyone have any thoughts on what the domain of the inverse cotangent must be? Somebody was saying something before I missed. Don't be shy. Somebody out there has the same thought you're having, hopefully. Draw this cotangent function. It's going to go through here. And Yes. Okay. So this is now the inverse cotangent function. So what's its domain?
Should it still be all numbers?
Yeah, absolutely. Right? I can pick an x anywhere I want along here. I'll get a value between 0 and 90 degrees. All right, the inverse, let's do secant inverse and cosecant inverse. These are a little different. You recall, if I were to graph when I graph the secant function, so that's the inverse of the, not the inverse, it's the reciprocal of the cosine function. The graph is going to look like this, having asymptotes wherever the cosine hits 0. Okay, so it's, I guess I should draw this as dotted, shouldn't I? This is actually my secant function. Okay, I want to pass the horizontal line test so I can see already I've got an issue here. So maybe I'll just take what's over here, all right? Restrict its domain to be greater than 0. And I've got a hole here, right? It's undefined at where? I guess I even need to write this. Secant of x is 1 over the cosine of x. So where the cosine is let's get that right. Secant of x is 1 over the cosine. Where's the cosine 0? I'm having a professor moment here. What's the cosine of 0? 1, right? So that's not it. It's the cosine of pi over 2. 0. Okay, so this must be pi over 2 here where this is going on. And then again, it's undefined here. I have a part of the function over here, but I'm going to have to cut it off because, again, it wouldn't pass the horizontal line test. Okay, so looks like I'm going between here and pi. Well, what does that look like? That looks like the inverse cosine, right? Between 0 and 180 or 0 and pi. Except that it can't be 90 degrees. I'll write this a little nicer here. I can say between 0 and 90. And then between 90 and 180. And I'm missing 90. Okay, that's my secant, inverse secant function. What about the domain? What functions can I plug into the inverse secant function? Or rather, what's the range of the secant function?
One to
it has to do with 1 and -1, but it's going to write those up there. Remember, remember the range of the sine function, right? The range of the sine function is what? It's from -1 to 1. The range of the cosine function is the same, right? -1 to 1. So 1 over the cosine, what's the range on 1 over that interval? In other words, if I take these as these x's, and I look at 1 over x, what do I get? Or what don't I get? Maybe if I draw the picture here. Could be the sine or the cosine. The cosecant function here is out here. So what values do these two functions have? These two functions. What value does this function have? If I say what y's does this function here hit? I drew in a line here at -1 and what's the range of that function? No, it's not negative. No offense. It's not -1 to 1. It's not in here. It's everything but -1 to 1. It's negative infinity to 1, to -1, and 1 to infinity. Okay, so that's the range of the secant and the cosecant function. So their inverses are going to have that as their domain. If your calculator had an inverse secant or an inverse cosecant button, which it does not, and you put in a value between 0 and 1, it's going to say error, or it might say domain. Okay, so, all right, we've got almost everything here. Secant, these both have the same domain. What's the range? Well, we're going to cheat here. You take a look. The secant and the cosecant are reciprocals, right? And they just so happen to have the same range. Their inverses have the same range, except for 90 degrees. The same thing happens with the cosecant function and the sine. The range is going to be what? It's going to be -90 to 90, but what's going to be eliminated from that function? Point in the middle, not equal to 0. You might, if you haven't written it down, you might want to write this chart down and think about it a little. We're really just thinking about, you know, our normal functions, sine, cosine, tangent, cotangent, secant, and cosecant, kind of in reverse. Okay. That's the hard part. Let's try and do something easy. All right, let's take a simple problem. Part A is find inverse sine of 1 over the square root of 2. Part B is find all angles where sine of x equals 1 over the square root of 2. First thing I'm going to ask is, what's the difference between those two questions? Think about it. Here I'm saying find the inverse sine, that's a function of this, right? It's going to have how many values? It's a function. How many values is it going to have? 1, yeah, okay. Find all angles, I guess all angles x, such the sine of x is equal to 1 over the square root of 2. How many of those are there? Infinite, yeah. All right. All right, let's take a look. Inverse sine, domain between -1 and 1, good. 1 over the square root of 2 is in there. Range minus 90 degrees to plus 90, or minus pi over 2 to plus pi. So we want to find an angle x equal to 1 over the square root of 2, where x is between minus 90 degrees and 90 degrees. Okay? Right? This is one of those, remember those angles? We have special angles we know the sines and cosines of. Anything that's 0 degrees, 30 degrees, 60 degrees, 45 degrees, 50 degrees. We know the sines and cosines of all of those. So the sine of which one of these is this? This you need to know. Pi over 4, or 45 degrees, yes. Sine of pi over 4 is 1 over the square root. So that's the answer to A. All right, for the second part, there's an easy part. We know that clearly anything that's pi over 4 plus 2 pi times some integer has to also be assumed, right? Because it's a periodic function. But that's not the only value. Let's see what I mean by that. If I draw the sine function, and I look here at 1 over the square root of 2, I draw a horizontal line. I'm going to pass through right here 45 degrees, right? Pi over 4. It's pi over 2. There's pi over here, pi over here. But I'm going to pass through another point here, right? Or this point, if you like. It's a little harder to figure out. What's this point here? 3 pi over 4, right? Three pi over 4 has the same what kind of angle as pi over 4? Reference angle. And the sine function in the first and second quadrant is positive. So we have pi over 4 is one of the solutions. And 3 pi over 4 is also a solution. That's all you'll get. You'll get 2 solutions like that. But then you get the rest of them. Right? 2 pi n plus 2 pi n, where, of course, n is some integer. And again, one way to think of that is, here we have this sine function going on forever. And at 1 over the square root of 2, we keep running into it. Right? So every 2 pi, right? Right, but then we have this other point. Okay, that was the inverse sine function. I don't want to erase my table quite yet. It might come in handy. All right, let's take a different function. The inverse tangent of -1. That's part A. And part B is all angles x such that tangent of x equals -1. Okay? So let's think about these angles again, because certain angles we know trig functions. We're not going to find one with a tangent of 1, are we? Right? Tangent is always positive in the first quadrant. But we can find something that has the tangent, one of these angles, the tangent will be 1. Anyone recall what the angle whose tangent is 1 is? Thinking of?
degrees.
45 degrees again, yes. Tangent of 45 tangent of 45 degrees. Okay. Okay. So where am I going to find the tangent -1? It's the first quadrant. Well, let me ask this question. What's the tangent in the third quadrant? Positive or negative? Negative? No. But you could guess. I mean, the sine and the cosine are both negative down here, right? But the tangent is the sine over the cosine. So the tangent is positive here. It's positive here. So we know it's going to be negative here, and it's going to be negative here. Okay, so this is the, this is 45 degrees, so we can see the tangent here is 1. What angle in the range of the tangent is -1? In the range of the inverse tangent is -1. That's a hard question. I mean, obviously I mean this angle here, right? It's that angle.
135.
Yeah, it's 135. Right? We know that tangent of 135 is -1. That's 3 pi over 4. Okay. That's one of 2 values in the whole circle in 360 degrees. Where's the other one?
7 pi over.
Okay, that's what here, 3 pi over 4 plus another pi, right? You could also call this what? Minus pi over 4. Would be same coterminal angle. Okay, so we know A now. A is tangent versus -1 is, what did we say, 3 pi over 4? And if I want all the angles, it's going to be 3 pi over 4 plus 2 pi n, right? But also 7 pi over 4 plus 2 pi n. If you look closely, we can write this a little more compactly, because 3 pi over 4 is just, well, 7 pi over 4 is just 3 pi over 4 plus pi, right? So these repeat every 2 pi, these repeat every 2 pi, but they're all 1 pi apart. So I could just write this as 3 pi over 4 plus pi n. Now, why does that make a lot of sense in kind of a weird way? Because we know that the period on a tangent is not 2 pi, it's pi. Right? So it's going to repeat every pi. Okay. Let's do a really simple problem. Well, simple or impossible. What is the inverse cosine of 0.346? Okay. What makes that really easy is you have to use your calculator. Before we had calculators, we had tables you'd look this up in. But we don't have any special angle that this is going to match. So checking our mode, I'm going to use degree mode. What do I get? Cosine 1.346. I get 69.757, something like that. Okay, that would be part A. will be part A of my question I've been asking. But now, I want to think about, right, I have an x value here, right, unit circle. This is 69 degrees. Where can I find my second angle? My second, well, it's just going to be minus 69.757. It's for the cosine, the inverse cosine. And then, if I want to get all the angles, I just add 360 and we're going to do a few more of these. We're going to do one more thing here. I'm going to repeat this because it's important. It's kind of odd. What if I ask you for the inverse secant of 3.6? Right. Clearly, there's no angle, special angle we know, so we're going to have to use our calculator. But unfortunately, our calculator does not have an inverse secant function. It's not that I know of. You might have some trig calculator that would. So we need some way to figure out what the heck this thing is. So here's how we do that. Let's just look at the inverse secant function of x. Well, we can write that by finding the secant of both sides. We can write that this way: secant of y equals x. Right? It's an inverse function. That's such an important step. I'm gonna pause for a second. Does everybody understand that? I mean, it's kind of trivial, but then if you don't get it, the whole thing kind of falls apart. All right. We don't really want to find secant of y. We want to find y, but we can notice right here that secant of y is 1 over cosine of y. So let's solve for cosine of y. Cosine of y will equal 1 over x. And now let's apply our inverse cosine function. Inverse cosine of y, inverse cosine of y, that's just y. So we have the inverse cosine of 1 over x. That's y. But y is the secant inverse. So the secant inverse of x is the cosine inverse of 1 over x. Now we know how to use our calculator. We're going to use the inverse cosine of 1 over 3.6. All right, we can do the same thing with the inverse cotangent, inverse cosecant. That's enough for today. We're going to do that again on Monday. This again is very tricky. All right. Thank you. It's okay, I'll stay. Almost the handwriting is the same on all of them. Only if you ask. No, I won't be there. I'll be in my office.
Okay.
You want to come by around?